Welcome back to my YouTube channel. My name is Mohammed Ubaid and this is another video of basics of structural analysis series. In this video we are going to solve another problem by using Macaulay's method. So in this question we have a doubly overhanging beam and at both free ends we have a point load of 5 kN and in the span BC we have a uniformly distributed load of 4 kN per meter. Now in this question we are going to find out the elastic curve equations, slope at free ends, deflection at free ends and the maximum deflection by using Macaulay's method. So let's get started with the video without any further delay. So we have a beam over doubly overhanging beam like this. Here we have pin support and here we have roller support, okay, and at this free end we have a load of 5 kilonewtons and at the other free end we have load of 5 kilonewton and in this span we have a UDL of 4 kilonewton per meter. Okay, so we have named this as A, B, C, D. So there will be a vertical reaction. Let us name this reaction as RV. There will be a reaction at C. So let us name this reaction as RC. Okay, now first of all we have to find out these reaction RB and RC. So as you can see here that the loading is symmetrical, and let me write the length of these segments. So it is 1 meter and for segment BC it is 2 meters and for segment it is also 1 meter. Okay, so as you can see here that the loading is symmetrical and the geometry of the beam is also symmetrical. Okay, so we can conclude that the value of RB will be equal to RC. Okay, and what is the total load? So total load on the beam is 5 point load plus 4 into 2 due to the UDL plus other 5. Okay, so it is 10 plus 8, it is 18 kilonewton. Okay, now we, as I have said here, that RV is equal to RC. So RV is equal to RC and it will be equal to total load divided by 2. Okay, so the total load is 18, so it will be 18 by 2 and it will come out to be 9 kilonewtons. Okay, now we have got the value of RV is equal to RC is equal to 9 kilonewton. Okay, so in this way you can find out the value very easily, or you can take the moment about B, then you will find RC and then you will use the sigma Fi is equal to 0 to get the value of RB. Okay, so this is the simplest way in which I have done this. So we have found out the reactions at B and reaction at C. Now we will proceed to our solution. So this is our beam. Now for Macaulay's method, the first reaction, or you can so we have got the reactions at B and C. Now we will proceed for our solution further. So here I have drawn the beam again. Okay, now the first equation which we write for Macaulay's method is this: EI d2i over dx square is equal to mxx. Okay, so mxx is the section, is the bending moment at section xx. Now in this problem we have a UDL in this segment BC. Okay, and we can see that this UDL is not continuous over whole span of the beam. Okay, so as I have told you in our previous video that in Macaulay's method and in the case of UDL, okay, in Macaulay's method and in the case of UDL we have to make the UDL continuous from the point of starting of the UDL up to the end of the beam. Okay, so in this beam the UDL is acting on this segment BC, but it is not continuous in the segment CD. So to apply this Macaulay's method, what I will do, I will make this UDL continuous from the point B to the point D. So how will I do this? So it is very simple. I will just add another UDL like this of 4 kilonewton per meter intensity. Okay, same which is of this UDL. Okay, 4 kilonewton per meter intensity. Okay, and I will add another UDL on the downward side of the beam which is of also 4 kilonewton per meter. Okay, and this UDL, as you can see, it is acting upward, and the UDL which I have applied on the upside of the beam, it is acting downward. So what I have done, I have made the UDL which is starting from point B to D. I have made this UDL continuous from B to D. Okay, and how I have done this, I have just applied two UDLs. One is on the upside of the segment CD, and one is on the downward side of the CD. So these two UDL which is applied, these two UDL will cancel out each other, and the resultant loading, or you can say the resultant UDL will be same. Okay, so there will be no net effect on the loading. Okay, so it is very simple, and you can do also. Okay, now we have made our UDL continuous. The first UDL is from B to D, and the ideal UDL which is acting is from C to D. Okay, so now I will write the equations. So the first term in the equation, for writing first term, we have to take the section in the segment AB like this. So this will be at a distance x, very simple. So the bending moment will be minus 5 into x. Minus 5 is the point load, and it is acting downward, so it will create hogging moment. That's why I have taken negative sign here. Now we will take the segment. This segment is this is section XX. Okay, now we will move this section XX in the segment BC. Okay, so now our section is in the segment BC like this. This is our section XX, and the distance will be, sorry, let me write it here, RB. So the distance will be x, and it should be very clear. We always measure the distance x from point A, or you can say from the starting point of the beam. Okay, so this is x, and it is measured from A. So the bending moment at section XX, at this section XX, let me erase this section from here so that you should not confuse about which section I am talking here. So this is our section XX now, and the bending moment at this section here will be due to this RB and due to this 4 kilonewton per meter UDL. Okay, so how will I add these two terms in this equation? So first of all, I will draw a vertical line, because there will be discontinuity in the loading at B. Okay, due to this reaction at RB, and due to this UDL which is applied on the upside of the beam in the segment CD, segment BC. Okay, so the other term will be due to this reaction RB, and it will be positive because the reaction RB is acting upward, so it will create sagging moment. So it will be RB into x minus 1. Okay, so what is x minus 1? So x minus 1 is the distance between this reaction RB. This is our x minus 1. So this is the distance, okay, between RB and the section XX. Okay, we have to take the distance, perpendicular distance between the force and the point at which we are taking the moments. Okay, now the other force which will be creating moment is this UDL. Okay, so the bending moment due to this UDL will be negative, because it will be causing hogging in the beam. So it will be 4 times x minus 1 square by 2. Okay, now this was for the segment BC. Now we have moved in our segment CD. Okay, so let me just erase these two things, 4 kilonewton per meter, because it will create congestion in this picture. Okay, so this is our 4 kilonewton per meter, we know. Okay, now I will just erase this section also, because it will create confusion. So this is, and also this x. Now we have moved our section in this segment CD. Okay, so now this is our section XX. Okay, and it is also a distance of x from A, and this distance will be RB minus 3. Okay, so RB minus 3. Now why 3? Because x minus 3 is distance 1 plus 2. Okay, so this is 3. Now we have to add the term due to this RC and due to this UDL, which is of 4 kilonewton per meter acting in the upward direction. Okay, so we will add a vertical line because there is discontinuity at C. Okay, so the bending moment due to this reaction RC will be sagging, so it will be taken as positive. So RC x minus 3. Okay, and the bending moment due to this 4 kilonewton per meter UDL, which is acting upward. Okay, this UDL is acting upward, so it will be also positive, so it will be x minus 3 whole square by 2. Okay, so this is the final equation for mxx. Okay, and we have to write here ei d2y over dx square. So let me name this equation as equation number 1. So we have got the equation for ei d2y over dx square. Now we will integrate this equation with respect to x to get the equation for deflection, to get the equation for our slope ei dy by dx. Okay, so it will be minus 5x square by 2 plus c1. I have told you earlier that the constant of integration will be written just before the first vertical line. Okay, now draw the vertical line, and the value of rb is 9, so let me put the value of rb. Okay, the integration of x minus 1 will be x minus 1 whole square by 2 minus, okay, so the integration for this term will be, so it will be 2 into x minus 1 whole cube by 3. Again vertical line, the value of rc is also 9, so it will be rc x minus 3 square by 2 plus the integration will be x minus 3 whole cube by 3. So this equation will be our equation number 2. Okay, now we have got the equation for our slope, so we will integrate this equation again. Integrate equation number 2 with respect to x. So now I will get the equation for our deflection. So equation will be 5x cube by, it will be 6 plus c1x plus c2, vertical line 9x minus 1 whole cube by, it will be 6 minus 2x minus 1 whole 4 by 12, vertical line plus 9x minus 3 whole cube by 6 plus 2x minus 3 whole cube by whole, it will be whole 4 because it has 3, so it will become 4, so it will be 12. Now this is our equation number, this is equation number 3. Okay, so we have got our equation for slope here, and we also have got our equation for deflection. Okay, now the task is to find out these two constants c1 and c2, because without these two constants we can't use this equation for finding out slope and deflection. Okay, so we will use our boundary conditions. Okay, so it is very simple to use these boundary condition. Okay, so this is our beam, and here, and this is our A, this is B, this is C, and this is D. So at B we have a pin support. Okay, so at B we have pin support, and at C we have a roller support. So as we know that at pin support deflection will be 0, and at roller support the deflection will also be 0. Okay, so the distance of B is 1 meter from A, because this span is of 1 meter, and this distance is of 2 meters, and this distance is of also 1 meter. Okay, so the value of x will be 1 at B, and the value of x will be 3 meters. Okay, at C. So we will use these two boundary conditions to find out our constant c1 and c2. Okay, now what I will do, I will just use this first boundary condition. So let me write it here. So putting x is equal to 1 meter and y is equal to 0 in equation number 3. Okay, so this is our equation number 3. Now the thing is, how many terms will I take? Okay, because this whole equation is valid for the whole beam. Okay, but I am just talking about this support B. Okay, so how many terms do I need to take? So I will just take these initial 3 terms before the first vertical line. Okay, because we are talking about segment AB. Okay, and these three terms are valid for the segment AB only. Okay, so just remember, when we are talking about this support B, we will take only these 3 segments. Okay, and okay, so let me first solve for for the support P. Okay, so what I will get, so y is 0, so on the left hand side we will get a 0, okay, and on the right hand side we will get 5 into 1 cube by 6 plus C1 plus C2. Okay, so you can solve it, so you will get C1 plus C2 is equal to 0.833. okay, so this is our equation number 4. Okay, now the thing is to use this second boundary condition. Okay, now put x is equal to 3 meters and y is equal to 0 in equation number 3. Okay, or you can also write use appropriate terms, which means that you should use only those terms which will be valid, okay, in that segment about which you are talking. Okay, so right now I am talking about this support C at where y is 0 at x is equal to 3 meters. So how many terms do I need to take? So I will just take the terms up to the second vertical line from here, because this whole equation will be valid from here to here. This whole equation is valid for the segment BC. Okay, and let me write here for BC, and this initial 3 terms will be valid for segment AB. Okay, and the whole equation from here to here, this whole equation will be valid for segment CD. Just remember these things. Okay, it is very simple. Just take the term up to the first vertical line for the first segment, up to the second vertical line for the second segment, and up to the third vertical up to the, or you can say the whole equation for the last segment. Okay, it is very simple to remember how you can take this term. Okay, so I'm just using these terms up to the second vertical line for segment BC, because this support is in segment BC. Okay, so you will get 0 on left hand side, and on the right hand side we will get 5 into 3 cube by 6 plus 3 C1 plus C2 plus 9 into 2 cube by 6 minus 2 into 2 to the power 4 divided by 12. Okay, so you can simplify this equation, and on simplifying you will get 3 C1 plus C2 is equal to this plus, okay, is equal to 13.167. so this will be equation number 5. Okay, now I will just write solving equation number 4 and equation number 5, which is fourth equation is this and fifth equation is this. Okay, so after solving these two equations, these two are very simple equation, you will just get the value of C1. so C1 will be 6.167 and the value of C2 will be minus 5.334. okay, so now we have got the values of constant, so we can write out our final elastic curve equations. Okay, so the equation for slope will be, so let me write here the equation, so it will be 5x square by 2, and the value of C1 is 6.167 vertical line plus 9x minus 1 square by 2 minus 2x minus 1 whole cube by 3. Okay, again vertical line plus 9x minus 3 whole square, this is 9 by 2. Okay, and plus 2x minus 3 whole cube by, it is 3. Okay, so let us name this equation as, so what was the number of equation? This is equation number 5. so this will be our equation number 6. Okay, now the other equation which will be have is for deflection. So the equation will become 5x cube by 6, and the value of C1 is 6.167x, the value of C2 is 5.334. okay, and now we will just draw the vertical line. It will be positive 9x minus 1 cube by 6 minus 2x minus 1 4 by 12. okay, again vertical line, and the term is 9x minus 3 cube by 6 and plus 2x minus 3 cube by 12. Okay, so this will be our equation number 6, 7. Okay, so these are the final equation for our slope, and this equation is for deflection. Okay, now we have got our elastic curve equation. So the other thing is to find out the other task is to find slope at supports. Okay, so slope at supports. Now let us see the geometry of the beam. So this is our beam. Okay, and this is the pin support, and here we have 5 kilonewton, and here we have 5 kilonewton, and in this segment we have 4 kilonewton per meter square. This is A, B, C and D. Okay, so the loading is symmetrical and the geometry of the beam is also symmetrical, because it is 1 meter and it is 2 meter, and this is also of 1 meter. Okay, so we are asked to find out the slope. Sorry, we are not asked to find out the slope at support. The task is to find out the slope at free end. Okay, so the slope at free end A and the slope at free end D will be equal, because the loading is symmetrical and the geometry is also symmetrical. Okay, but the thing is the sign will be different, because if you just draw the reflected shape of the beam. So let me draw the reflected shape of the beam here. So this is our pin support and this is our roller support. So the beam will deflect something like this. Okay, now if you want to find out the slope at A, so this is our A. So what you will do, you will draw a tangent like this. Okay, so this angle, this angle is our theta A. Now you can see here that this angle theta A is, this angle is anti-clockwise. So anti-clockwise means, in our sign convention, anti-clockwise slope is taken as positive. Okay, so this theta A should come positive and this theta D should come negative. Okay, so we will verify this. Okay, so we will use equation number 6 to find out the slope at A. Okay, so first of all we will find out the slope at A. Slope at A means x is 0. Okay, so how many terms do we need to take for finding the slope at A? Okay, so we will just use these two terms before the first vertical line. Okay, because we are talking about this segment AB. Okay, so the first term is minus 5x square. So let me write it here, EI dy by dx at A. So minus 5 into x is 0, x square by 2. Sorry, it will be 0. And the other term, which is C1. Okay, so the value of C1 we have just found out 6.61. Okay, so here we will get the value of dy by dx at A, or you can say theta at A will be 6.167 EI. Okay, so as you can see here that this value is coming out to be positive, which means that our assumption, or you can say our deflected shape, is correct. Okay, and if you measure the slope at this and D, it will just be opposite. Okay, it will just be opposite of this equations, of this value 6.167. okay, and you can also find out the value. So slope at D, dy by dx at D will be equal to 1 by EI. Okay, so the distance of D is 4 meters. Okay, so at x is equal to 4 meter. Okay, I will just put the value of x is equal to 4 meter in this equation number 6. Okay, so I will use all the terms up from first term to the last term, because now I am talking about the last segment, segment CD and the point D of this beam. Okay, so now let me just put the values. So it will be 5 into 4 cube by 6. Sorry, this will not be cube. This will be 5 into 4 square by 2, plus the value of C1 is 6.167. Okay, plus 9 into 3 square by 2 minus 2 into 3 cube by 3 plus 9 into 1 square by 2 plus 2 into 1 cube by 3. Okay, so let me just calculate these values. So after calculating, you will get the value of minus 6.167 divided by EI. Okay, so as I have told you earlier that these two values theta A and theta D will be same, but their sign will be different, because at A the slope is anti-clockwise, okay, and at D the slope will be in this direction. Okay, so if we draw the tangent at D, so this is our tangent. Okay, so the slope will be slope will be clockwise. Okay, so this will be negative as according to our sign convention. So this is for the slope. Now the other task is to find out the deflection. Sorry, let me write it again. The deflection at free end. Okay, so it is also very similar to the case of slope, because the loading is symmetrical and the geometry is also symmetrical. So the deflection which we will be getting at A, it will be same at D. Okay, so we have just to find out the deflection at A. So we will use this equation number 7 to find out the deflection at A, and we will use only these three terms up to the first vertical line, because we are taking point A which is in the segment AB. Okay, so we will just put the value of x is 0 in this in these three terms. Okay, so let me just find out the value of deflection. So EI YA. Okay, so its value will be the first term will be 0 and the other term will also be 0. We will only have minus 5.334 EI. Sorry, EI we have written here. So the value of YA will be minus 5.334 divided by EI. So this is the deflection at our free end, and this will be also equal to deflection at D. Okay, and the sign will remain negative, because as you can see here that both the points A and D are deflecting downward. Okay, so downward means the sign will be negative according to our sign convention. Okay, so this was our deflection at free ends. Now the last task for this tutorial is to find out the, or you can say as I have written, maximum deflection. So this is our last task. Now let us move to our geometry again. So this is our deflected shape. Now in this beam the deflected shape is like this. Okay, so at which point the deflection can be maximum? Okay, so as you can see here, the deflection can be maximum at A, the deflection can be maximum at D, and the deflection can be maximum in this mid span, at this point, at the mid span. Okay, so let us name this point as E, which is in the mid span of the beam at here. Okay, so this is our E. Okay, so at A and at D we have found out the deflection. Okay, we have just to find out the deflection at E, and if this value is more than the deflection at A and D, which means that the deflection is maximum at E, otherwise the deflection is maximum at A and D. Okay, so let us just find out the value of deflection at E. So the distance of E is the distance of E is 2 meters, because it is in the mid of the beam. Okay, so I will just put the value of x is equal to 2 meters in this equation number 7. And how many turns do I need to take? So because I am considering now this segment BC, so I will just take the turn up to the second vertical line. Okay, so now I will just put the value of x is equal to, at E, x is equal to 2 meters. Okay, so after putting the values you will get EIYE minus 5 into 2 cube by 6 plus 2 into 6.167 minus 5.334 plus 9 into 1 cube by 6 minus 2 into 1 to the power 4 by 12. Okay, so after solving these values you will get 1.667 divided by EI. Okay, so this value is positive, which means that the deflection will be upward. Okay, as you can see here in the deflected shape. So at E the deflection is upward. Okay, but this value of deflection at E is less than the value of deflection at A or at D. Okay, so which means that the deflection is maximum. So let me write it here. Maximum deflection is occurring at A and D. Okay, so this is the final answer for this problem. I hope you will like this solution. If you like this video, please subscribe to my channel and share this video. If you have any confusion regarding any point, please comment down in the comment box and I will try to answer all your comments as soon as possible. Thanks for watching. We will meet in our next video.